Hi, and welcome to H1.5 Centripetal Acceleration and Tangential Acceleration. In this lesson, students will be able to describe the difference between and calculate centripetal, tangential, and angular acceleration. So way back in Unit 7, we did talk about centripetal acceleration. That was only for instances where it was in uniform circular motion. So this says tangential speed is constant because the object is in uniform circular motion. You can see it's moving around, constant speed. Okay, the tangential velocity is changing because the direction is changing, and velocity is a vector quantity, magnitude and direction. And as you can see, this vector arrow continuously changes. Since velocity is changing, there is an acceleration. That's the definition of acceleration, is when you change your velocity over a certain period of time. In this case, it just happens to be that the change is in the direction. The object is being pulled towards the center, so it's accelerating towards the center. There is a centripetal acceleration. So this is as far as we went. But now we have rotation, where you're changing the speed of the rotation, which means your tangential speed is changing. So if tangential speed is not constant, the object is in non-uniform circular motion. So we're going to rotate. It looks like we're going to go clockwise. Is that positive or negative? That's going to be negative. But the acceleration, the tangential acceleration, is going opposite that velocity. So are we going to speed up or are we going to slow down? Let's see what this looks like. We're slowing down. It's non-uniform circular motion now. The tangential velocity is changing because the direction is changing and the tangential speed is changing. Since the magnitude of the tangential velocity is changing, there is now a tangential acceleration in addition to the centripetal acceleration. See these two? Whoa, nice. Wow. All right, so let's look at this a slightly different way, thinking about angular velocity and angular acceleration. Tangential speed is constant if the angular velocity is constant and the object is in uniform circular motion. Looks something like this. Constant angular velocity, same amount of rotations per second, and it's uniform circular motion. The tangential speed isn't changing. However, if the angular velocity changes, that means the tangential speed is changing because you're spinning either faster or slower, so your tangential speed is changing, and the object is in non-uniform circular motion. Interesting. All right, so we have here the direction of the angular velocity. Remember the right-hand rule? We did that in one of the slides. You take your right hand and you curl your fingers in the direction of the circle, and your thumb points towards the vector, the angular velocity vector. So normally we draw vectors like arrows, but the vector is going into the screen here, and we use an X to represent when the vector is going into the screen and a dot to represent when it's coming out of the screen. It's kind of like you have a bow and arrow. So this is the side view of the bow and arrow. But if you were standing right here, maybe all you would see is the point of the arrow and it's coming towards you. So that's the point and it would be coming towards you. If you were standing behind the arrow, then all you would see are the feathers of the arrow. And the feathers are oriented in an X direction like that. So it's going away from you into the page there. So if you use the right-hand rule, then the angular velocity is going into the screen at this point. And it says the angular velocity is changing because the object is slowing down, making less revolutions per second. Let's see what it looks like when it slows down. All right, so they're slowing down. Since the angular velocity is changing, there is an angular acceleration. The object is slowing down, so its angular acceleration is in the opposite direction. Remember we said how if the acceleration is in the opposite direction of the velocity, you slow down? So how would you represent on this screen, how would you represent the direction of the angular acceleration? You could pause the video and think about it. we would use a dot because that's going in the opposite direction than your angular velocity. So that's what it looks like when it's slowing down. If it was speeding up, they would both be X's or both be dots. That's just like a little side note there. So what is happening to the centripetal acceleration as you're slowing down? You could pause the video and think about that. That's a good question. Well, don't forget, we said the centripetal acceleration is equal to v squared over r. This equation's coming back in this unit, okay? So if your tangential speed is decreasing, what's happening to your centripetal acceleration? It's also decreasing. Interesting. Very good. So this is, in a nutshell, the direction of the vectors for your tangential acceleration, your centripetal acceleration, and your angular acceleration. It's coming out of the page in this case. So what happens if we try to add these vectors together? What you can do is do the parallelogram rule or add the vectors head to tail, and you get what's called the total acceleration. That's the vector sum of the tangential acceleration and the centripetal acceleration. Remember, this is our good old friend v squared over r, and we just found an equation for the tangential acceleration using the switcheroonie interchanger. So we got some nice equations here, and our good old friend vector addition is coming back into play. So how can we relate centripetal acceleration to rotational kinematics? Well, we know, again, that the centripetal acceleration is equal to, what is it? We already learned it in Unit 7. V squared over r. So let's make that the tangential velocity. And what do we know about the tangential velocity? Let's try to make this into the rotation. So what is the switcheroonie for the tangential velocity? Pause the video. Try to figure it out. Okay. It's r times the angular velocity, r omega. So now we could plug in, every time we see a VT, we plug in r omega, and now we're like looking at the centripetal acceleration in terms of some angular velocity. So this looks a little bit messy. We could clean this up a little bit. Let's get rid of this, the squared stuff. All right, let's square both things in there. And then we have a lot of r's there, so we could cancel out one of those r's. Nice. So the centripetal acceleration is equal to r times your angular velocity squared. Nice, that's good. Now remember, this needs to be in radians per second because we used this switcheroonie when we derived this formula. So this also needs to be in radians per second. Where is this handy switcheroonie for a centripetal acceleration on the reference table? It's located right here in the section where it says it has to be in radians. So we need omega to be in radians per second in order to use this formula. So here's a little review of the concept here. It says, what direction is the centripetal acceleration? Pause the video and think about what direction you would make the arrow for the centripetal acceleration. Hopefully you said, this is always true. The centripetal acceleration points towards the center of the circle. Now for non-uniform circular motion, all right, what direction is the centripetal acceleration? Still towards the center. But what direction is the tangential acceleration? Let's say you're speeding up. So your tangential velocity is pointing this way because we're rotating around this way. So we know our tangential velocity is this way. And I'm going to tell you that you're speeding up. It's non-uniform now. What direction would the tangential acceleration be? That's right. It's going with the velocity. So if they point in the same direction, that means you're speeding up, as I said. And then what would the total acceleration of those two vectors look like? If the question asked you, what is the total acceleration? What does that vector look like? We're going to add the centripetal acceleration and the tangential acceleration to get the total acceleration of this object. And it looks weird because we're in non-uniform circular motion now. All right, before it was straightforward. It's just straight towards the center of the circle. But now we're speeding up our rotation. We're getting faster. Our angular velocity is increasing. So we end up getting a total acceleration that way. Nice. All right, so let's do an example problem. It says, starting from rest, the thrower accelerates the discus to a final angular speed of positive 15 radians per second in a time of 0.270 seconds before releasing it. During the acceleration, the discus moves in a circular arc of radius 0.810 meters. Find the magnitude of the total acceleration. And if we have room, I'm going to find the direction as well, that angle phi. Why did they use the angle phi for this one? I wonder. Maybe because theta is already being used by the angular displacement during this unit. So yeah, don't get confused by that. Okay, and then the other thing I wanted to say was this is positive. So what direction is positive, clockwise or counterclockwise? Positive is counterclockwise, so the diagram is doing a good job of representing the problem. If you want, you could pause the video and try it on your own. So let's start by writing down some of the given information. They tell you that you're starting from rest, so you have 0 radians per second initially for your initial angular velocity. Your rotation speeds up. You have a final angular velocity of positive 15 radians per second in a time of 0.270 seconds. They even tell you the radius is 0.810 meters, and they're asking for the total acceleration. Now, to find the total acceleration, that's this vector here, let's find the tangential acceleration and the centripetal acceleration, and then we'll do the vector sum to find the total. So we are going to find, let's find the centripetal acceleration first, because we just learned a nice switcheroonie for that. And then the game plan is to find the tangential acceleration. Okay, so the switcheroonie for the centripetal acceleration is equal to r omega squared. Again, making sure that our omega is in radians. It is. So we just substitute in our values. 0.81 times 15 squared. The centripetal acceleration is equal to 182.25. What are the units for centripetal acceleration? They're going to be meters per second squared. And just as a side note, radius is in meters. Omega is a radian per second, but that's being squared. So this becomes a radian squared per second squared. We said radians are like effectively unitless, so that becomes a meter per second squared. Kind of nice how that works out, right? Okay, so now we have, that's good. We have the centripetal acceleration, and we're going to find the tangential acceleration. I would like to use this formula. I would like to use a switcheroonie. This is the only formula we really have for tangential acceleration on that rotation reference table. But we don't know what the angular acceleration is. I wonder if we can find it. Yes, we can. Okay, so the angular acceleration is equal to your change in angular velocity with respect to time, which is the final minus the initial over 0.270. Your angular acceleration is 55.5 repeating radians per second squared. Then we just plug that in to our formula over here. The tangential acceleration is equal to 0.810 times the angular acceleration that we just found. And you get a tangential acceleration of 45, exactly, 45. What are the units for tangential acceleration? They're going to be a meter times a radian per second squared. So that just is a meter per second squared. And I just realized I used up all this space. So that's nice. We have the tangential acceleration and the centripetal acceleration. I'm going to write them in over here, and then we'll do the vector addition. Okay, so now we know that, well, I guess I could write. All right, so this is going this way. The centripetal acceleration is 182.25 meters per second squared. And then at this point, the tangential acceleration is less than that, 45 meters per second squared. We want to add these two vectors together. Now, how do you add vectors? Head to tail. And these are tail to tail right now. So you would rewrite this one. You could do the parallelogram method if you want. And then this is the resultant vector. This is the total acceleration. So you do what we normally do for the magnitude of the resultant. So the total is equal to the square root of AC squared plus AT squared. That's just the Pythagorean theorem. So you get a magnitude of 187.7 meters per second squared. And if we wanted to, we could figure out what this angle is here as well by doing the inverse tangent. Remember, because we know what this leg is. This is opposite, this is adjacent. So opposite, adjacent, that's tangent, but we're solving for the angle, so we'll use the inverse tangent. And you get 13.9 degrees. Remember, the tangent acceleration is opposite, so we put that on top. So your final answer for the total acceleration is 187.7 meters per second squared, 13.9 degrees. You could say like above the horizontal. This looks like, if this was north, this looks like it's 13.9 degrees north of west. Very nice. Anyway, that's about it. Thanks for watching and have a great day.